Well, I'm not going to say that that game went the way that I wanted it to, but I didn't tear my Achilles off, I guess. That's positive, right? Hey, we lost. Sorry for those that I let down. I gave it my best. Just couldn't get baskets to fall and don't know why. So, anywho, let's get back to something a little more serious, if we can, which is your review for your test. So remember, we are passive and active transport. I basically at this point have taught the same material yesterday. So, I mean, here you are. It's Tuesday. You're giving a review. Wednesday, we won't have it because of those people that are doing dance. So, Thursday will be your test. Nothing else at this point in time for you to do besides know the information that I just talked about yesterday when I went over the same stuff. And then today when I'm basically telling you what's a discussion question or whatever else it is. Okay? So, stay on top of it. Do the best that you can. Um, Prepare yourself well, and you'll be fine. You're given enough time. It didn't matter that I wasn't here for the second half. You were here for the first half. I technically am here for the second half because it's still just me answering or teaching you. I know I can't answer questions, but again, there's nothing to be asked of me that you can't rewatch in this video and get a concept of to pass this test. Okay, so I want you to be positive that you're going to do well. Unlike I'm positive that I'm going to survive after the fact that I was gassed 4 minutes into the game and I've got to go to Colorado in 2 days. So I feel like there's a chance that I'm not coming back. But hey, I'm going to try my best. And maybe next year I'll have some more three-pointers actually go in the hole. I think I wasted them all in warm-ups. I think it's what happened. And it is what it is. Nothing I can do now, right? Besides just hope that one day I will recuperate and get over that and not feel like I let my team down so bad, you know? So I think a few of them went all the way down into the hole and touched the net and then came back out. But hey, you win some, you lose some. Look, here's the reality of things, right? The reality of life. We don't always get to do what we want to do. We don't always win when we want to win. And sometimes you do the best that you got and it's still not enough. And I know that's not fun. I know that's not something that you want to be told. And I know that most of our parents don't tell us that. It's not that they don't love you. It's that they love you enough that they're trying to shield you from those things. But the reality is that it's difficult sometimes to live life and for you to get out of it what you feel like you should get out of it. You study sometimes for an hour for a test and you feel like you deserve a good grade and it doesn't work. Sometimes you don't study and you do better. That kind of stuff happens. But it doesn't take away from the fact that we still have to fight, we still have to work hard, and we still have to kind of take our losses and learn from them. You know, it's an interesting statement. We were talking to some of the girls today, you know, after the game, and you know, some people were wondering whether or not Coach Cunningham was, you know, why he wasn't laughing. And I mean, he made a very good point. He very simply just said, "I just lost by 9 points." I want us to get to the point at CA where no one's complacent with losing. I don't want you to be complacent with losing on a football field. You better not be complacent with losing on a soccer field or a baseball field where I'm at. I don't want you to be complacent with losing in the game. I want you to be complacent with losing in the classroom. Will that happen? Yes. Do I want you to learn from that? Yes. Do I want you to give up because of it? No. It's just that honest truth there. And y'all figure that out for yourselves. But I want us to get to the point where you're just not pleased when you do poorly. And not with me or with your coach or with whatever else, but with yourself, with the situation. And again, that may happen and you may overcome it. Great. Excellent. Fine. It may happen and you didn't win that day. That's okay too. It's not the end of the world. We're going to survive. We'll get through it. It's just the reality of the way life is. It's just kind of how it is. So let's talk about active and passive transport. I tried to actively transport the basketball goal into the goal, and it did not work. Passive transport apparently was not going to work because I was dying. Needless to say, I'm out of shape. And that's just is what it is. So let's do some looking. I'm going to pull up for us if we can. Let's see if I can do my shrink me down. And let's see if we can't get ourselves into some homeostasis. Right. Nice. Okay, so here we go. Passive transport. Again, look, same slides I did yesterday. I mean, I kind of reviewed again shortly yesterday, but I want to be more specific today as we go over this review. Let's see what we got here, okay? Apparently not clicking. There we go. All right, so homeostasis, know the definition. Should not be any question, right? Nothing but a balance is all that means. Know what types of things can come in and out of a cell. H2O, CO2, O2. If I were to ask you, let's say Wyatt, and I kind of look the opposite way because of how the camera does, right? Or is it backwards or forwards? I think it's this way maybe. Wyatt, what I want to ask you is this. When we think about the ideas of H2O, CO2, and O2 being small and being able to pass through, which of these things passes through a membrane slower? Glucose, C6H12O6, or oxygen, O2? Great work, Wyatt. You did excellent, right? It's glucose. Why? It's a larger molecule. So this is something that you can see very simply how I would ask questions about this. I could ask you to list the three things off for me. I'm not going to. I could give you two of the three and put it on a multiple choice. Fine either way. I could ask you, just like I did, about another molecule that's not on here and say, does it also go through by passive transport? I mean, what if I gave you, I don't know, what if I gave you ATP and said, which of these four does not go through by passive transport? Well, I mean, you know three that do. It's obviously the fourth one. I don't care if I give you something that you don't even know what it is. Okay? So don't overthink it. Water, CO2, oxygen, very small, come in and out of there pretty easily. Okay? Not a problem. Because they don't expend energy, what's that called? Passive transport. You need to know the differentiation between passive and active transport. If you miss this question on my test, I'm going to cry a little bit inside. I really am. Maybe not as much as I'm crying about my missed baskets, but I'm going to cry. Passive transport requires no energy to move things inside or outside of a membrane. Active transport requires energy to move things inside or outside of the membrane. So I got to write down. Okay? We're all good. Everybody's good on this slide. No questions asked. Nice job. Excellent work, everyone. All right. Diffusion. That is the movement of molecules from an area of what? Low to high, high to low. High concentration to low concentration. Don't miss this. I'm going to ask you this question on the test. It's going to be on there in a multiple choice. You're going to have the ability to say to me, well, it's got high, low, and low, high, coach. I don't know which one. It's moving in diffusion from areas of high to areas of low, trying to create a balance or what we call equilibrium. Okay, that's all it's doing. So just know the definition. The difference in concentration from the outside to the inside is what we call a concentration gradient. That's what we mean when things go down a concentration gradient, meaning moving from high to low, or against or up a concentration. We typically say against a concentration gradient, which means we're going from low to high, okay, which is not normal. And notice what drives this function, what drives diffusion, kinetic energy of the molecules. Their own desire to move. That's what that means, okay? So don't be confused about diffusion. You all got this, all right? Okay, rate of diffusion. I'm going to ask you very simply what types of things can change the diffusion. And this will probably be a listing question on my test. Temperature, molecule size, and molecule type. Temperature, molecule size, and molecule type. They're written right up here. You can see them right here on your presentation. If you can see this from the front of the room, I don't know. But right here, okay? Don't have a laser pointer to print with, actually. I think I probably could do that, to be honest. All right, so just don't miss that. Let's see if I can. An arrow. What? That doesn't do anything. Laser pointer. Hey, up here, everyone. Yeah, look at this laser pointer. All right, so there's your laser pointer, okay? Rate of diffusion, temperature, molecule size, and molecule type. All right. Molecules are going to diffuse faster if they're higher or lower temperature. Higher. Molecules are going to diffuse faster if they are large or small. If they're small. Molecules are going to diffuse faster if they are charged or uncharged. That's right. Uncharged things will diffuse faster than charged things. Okay? So, again, remember, diffusion always goes down the concentration gradient. Okay? It will continue to do that until we create equilibrium. Remember, that's, straightforward. Let's move this back over. I can't do it because I just got to go back to automatic so that I can move this over. Equilibrium. Okay? Off the slide. There I am. All right, so equilibrium. Don't miss that. Equal distribution known as equilibrium. All you got to know is the definition. Okay. Try to scoot myself over. Okay. All right. Here we go. Water. Water can diffuse. It's called osmosis. Okay. Water can diffuse. It is called osmosis. Is all diffusion osmosis? No. Is all osmosis diffusion? Yes. All osmosis is a type of diffusion, but it's about water. Not about other things. Not about oxygen. Not about CO2 or any other thing that we talked about. All right. Again, this is the big point that we can't miss, and I don't want us to be confused about this at all. This is the idea that osmosis is the movement of water from an area of low solute to high solute. Low solute to high solute. Okay? Water will cross that membrane until they have the same solute concentrations. They won't necessarily have the same solutes, but the same solute concentrations. Okay? Again, let's go big time here. Here we are. Again, don't overthink this. Okay? At all. There's no reason to overthink this. There is a cell. This cell has a 5%, I'm going to say salt because that's the solute in this case. Okay? No big deal. It's a 1% on the outside. So, Ms. Olivia, can you give me an answer here? Which way is water going to move in this case? Nice job. Excellent work. 1 bonus point to you. Not really, but thanks for getting that right. Water moves inside. Why? As water leaves this, what happens to this number? It goes up. As water enters into here, what happens to this number? It goes down. And it will do so until it gets to an equilibrium. 3% on each side, right, in this case. I'm not going to ask you any number type thing where you have to try to tell me that it's going to be 3%. But you get my point, okay? This idea is not hard. Water moves from low solute to high solute. Okay? This is the entirety of everything that we're discussing when it comes to diffusion, when it comes to hypertonic, hypotonic, isotonic. All of that has to do with this. So you have to have this concept. If you are missing the concept of how diffusion for osmosis works, water, you can't pass this test. There's too many questions related to it. So this is how it moves. Okay? If it was opposite of this, right? I should have had my eraser, but it's too far away and I don't want to get up. My legs don't work right now. They're pretty much still jello. It's 1% in here. It's 5% out here. What's going to happen? Cell's going to do what? It's going to have water leave it. This is what we call a what? What type of solution? Hypo, hyper, or isotonic solution, Wes. Wes, this is a hypertonic solution. What does this do? This cell is going to shrink like this, right? Can die, crenation, right? Remember all this? So again, don't miss the concept, right, that is happening for where water is going to go. And again, why would the cell want to move water? Instead of moving some salt in here and making these equal, why on earth would it want to move water? Because it's free. It requires no energy. It's passive transport. So it can freely do that. So if it does so, we can balance those things out because it wants to create a balance of all things. It doesn't want just balance of water inside and out. It wants a balance of solute concentrations in there and things, gases that are in and out. It doesn't matter. It wants a balance of those things, and we're giving it in this case. Okay? I'll be back to this in a second when we talk about our hypers and hypos here in just a moment after I get to that point. Okay? Okay. Here's our hypertonic solutions. Okay? On my test, you will draw these three pictures. Nobody panic. Stop with the, oh, how am I going to do it? Hold on. Just settle down. Again, I'm not trying to hurt you. I'm not. I know that's like a surprise to some of us, but I'm not. Ready for my drawings? Get ready. It's going to be fantastic. All right, here we go. See if I can move us. All right, so you're going to draw for me what a cell does, an animal cell does in a hypertonic solution. So it's going to say hypertonic. You have a cell. You are going to show that all the water leaves it and the cell shrinks. You're going to show me a hypotonic solution. You're going to show me that all the water, notice there's two lines. This keeps you from being confused. This keeps me from wondering what's happening, and it makes it very simple. This is a hypotonic solution. All the water comes in, and what's this cell going to do? Just draw me a bigger circle. It's okay. You're going to draw me an isotonic solution. You have water that comes in and water that goes out. And a cell that's as close to the same size as your current hands can draw, since some of us are not artsy. There you go. That's 10 points on my test, guaranteed. Hypertonic, what does it mean? Let's look at a definition if we can. That's on our previous slide that we just had, right? Hypertonic. The solute concentration is greater inside or outside. Think the water's leaving. So that means that there is a higher concentration on the outside. That's why it has to leave. It goes from low to high solute. So hypertonic means that the solution on the outside has a higher solute. Hypotonic means the inside of the cell has it. Isotonic means it's equal inside and outside. That's all that means. No big deal. Then we have two different types, at least, of cells that we're going to deal with. Here, what happens to a plant cell? You won't have to draw this. What happens to a plant cell in this hypertonic solution? It shrinks as well. Plasmolysis. What happens to this one? Turgor pressure, right? Water fills inside of a plant cell, and a plant cell does not swell like this. It has a rigid cell wall, which keeps it from doing so. And because of that, it creates turgor pressure, and helping it to stand up gives it more structure. Does not work out that way for an animal cell. An animal cell is basically looking to lyse and explode because there's so much water in it. Not a plant. Isotonic solution. Animal cell's happy and loves it. Plant cells, what we call flaccid. It's weak. It doesn't have enough water pressure. Pretty straightforward, right? Hyper, hypo, iso. Plant, plant, plant. Hyper, higher concentration outside, so water has to leave, causes the cell to shrink. Hypo, higher concentration of solute inside the cell, and it causes water to enter in, makes the cell swell. Isotonic, same concentration inside and out. Water can freely pass in and out, and it pretty much stays the same. Cell looks like this, if it's an animal cell. If it was a plant cell, it would shrink the same. If it was a plant cell over here in isotonic, it would look flaccid, so it would not be as strong. If it was a hypotonic solution, which is what plants prefer, it's going to look like a perfect cell, but it's going to be rigid. It's firm. So it has the ability to stand up. Remember, plants don't have skeletal structures. They need all the help they can get. Cell wall, turgor pressure. That's what they got. It's like 4 of your next slides, 4 or 5 of your next slides, right? That's all you got to know. If you can do this, you can answer a ton of questions on my test. A ton. Let me get myself out of the way. So, know your definitions. Hypertonic, higher concentration of solute outside. Okay? Water is going to do what? Leave, causes cells to shrink. If in an animal cell it happens, they lose too much water, it's called crenation. Plant cells, plasmolysis. Just got to know the definitions. Nothing you can do besides memorize the definitions. Don't get them backwards. Plasmolysis, plants. P, plants. Crenation is animals, okay? Animal cells. Again, that's not cremation, that's crenation, okay? Let's definitely not miss that. All right? Hypotonic, higher concentration of solution of solute inside the cell, causes water to do what? To move into the cell. You can see that on this right side over here as an example, okay? If this were to happen, they can lyse. That's the busting of a cell. The busting of a cell is lysing. I don't want you to miss this. Animal cells can burst for other reasons than taking on too much water, okay? If they take on too much water, we call that cytolysis. Lysing is basically the bursting of it. That's what that means, to lyse something. The busting of a cell due to taking on too much water is called cytolysis. Why will this not happen in a plant cell? Again, plant cells in hypotonic solutions are happy because they take on water, they become turgid, they have strength and structure, and they're perfectly fine. All right? Everybody's good there? Good. Again, you're just going to give me drawings of these things. Should not be complicated. All right? Everything else you're looking at basically is multiple choice, true, false type questions, whatever else it is. Okay? All right, isotonic solutions. Equal on the outside and inside, and because of that, water moves freely back and forth, and everything looks perfectly fine, especially for an animal cell. For a plant cell, not so much because it's weak. It's not dying, but it's just weak. It's flaccid. It does not have strength and support. It needs strength and support, okay? That's what this tells you. So plant cells prefer hypotonic. Animal cells, notice down here, prefer isotonic. What is created by this? Turgor pressure, right? Sit right here. Turgor pressure helps do this. Notice this, as plant cells take in water and become turgid, the pressure, turgor pressure within the cell increases, okay? Now these two words, put them together. Turgor pressure. Basically, we're squeezing, look at this. We're squeezing against these cell walls so that this thing can have some structure and stand up. Okay? Should be no questions. All right? Turgor pressure. We all good? Hopefully we're all good there. All right? Again, I can't really explain any better than that. Now, facilitated diffusion is another type of passive transport. You have to get this in your mind. Look, it's written right here down at the bottom. It's considered passive. Again, why? Anything that's passive means what? It does not require any energy. Primarily, look at what we're doing. We are helping to move what? Glucose across this membrane, and we do so through either protein channels or through our carrier proteins. Why would we want, again, to get glucose into the cell without spending energy? Well, glucose is what we use to make energy. So because of that, what do we not want to do? We don't want to blow more energy to get that energy, right? We want to get free energy. Everybody wants free energy, you know? We want to, borrow the electricity, go into our neighbor's house and let them pay for it. That's what we want to do. Don't do that. But that's what we want to do. Same thing happens here, okay? We want to get free energy. We don't want to have to spend money to get energy. We want to get it free. And so we're trying to bring in things like glucose and some other things, but things like glucose without spending energy to do so. We call that facilitated diffusion. Facilitated diffusion, okay? You got to know that, all right? Like aquaporin is a good example. It's not on your test, but aquaporin is basically a facilitated diffusion of water. It allows water to freely come in and out, like in a hurry. That's what that is. Now, water can pass through the membrane, but it's a highway. It's a quick process, is what I'm getting at, right? In case the cell needs to gain or lose water quickly. Okay, facilitated diffusion because it does not require any energy expenditure. Okay, so you're halfway home. I show me at 24 minutes. I'm sure Isaac's asleep, but we're all here. Okay, so let's just keep pouring along. Active transport. Anybody want to take a stab in the dark what this means? Active transport requires what? It requires energy. Okay? That's all it is. Requires energy. So notice these things. Good example of this sodium potassium pump, right? Moves what? Moves sodium, right, and potassium ions through the cell membrane. Those are ions. They don't want to go through the membrane on their own. They got to have help. To have help, they got to have energy expenditure, which is ATP. We got to burn energy to get them in and out. That's what we're doing. Okay. Notice this. It utilizes ATP to move materials against the concentration gradient. So what are we doing? We're moving things from what? Areas of low to high concentration. You know why? Because there may be 3 pieces of potassium floating around on the outside, and we want 2 of them to come in through our sodium potassium pump. But we already got 15 inside because we need all that potassium to help continuing to rebuild our ATP or whatever else it may be, right? So I don't want you to miss the fact that we're moving against the grain. We're not going with it, okay? And because of that, we're spending energy to do that. If we could go with it, right, it wouldn't cost us energy, and we'd be back to passive. But in this case, we're not, all right? So remember our sodium potassium pump. I've already kind of talked about this, but we're going to have 3 sodiums. If I can get my hands in their way. We're going to have 3 sodiums, okay, come in, and we're going to have 2 potassiums go out. Let me rephrase that. I got us going backwards. We're going to have 3 sodiums go out. We're going to have 2 potassiums come in, okay? Sorry about that. So our 2 potassiums are going to move in. Our 3 sodiums are going to move outside the cell. You got to know the numbers. Got to. I'm going to ask you about it, okay? Basically, what's going to happen is, notice what it says. These ions are exchanged. Charges within the outside of the cell are changed. In other words, we're changing the positives and negatives. Look, if I took 3 positives and shoved them outside and took 2 positives and brought them inside, did I not have a net gain of positives on the outside? I did. Did I not have a net gain of negativity on the inside? I did. Okay? So we're basically trying to balance that to some degree. And as we do so, we call that the membrane potential. My neck's killing me. I'm pretty positive I'm going to be in a neck brace while I'm in Colorado. Anywho, could have torn an ACL too, apparently. We did that one also. So, again, this is called a membrane potential. This is the difference between that positive and that negative. So, again, think, if I'm putting 3 positive things outside and taking 2 positive things inside, I've had a net gain of positivity on the outside and a net gain of negativity technically on the inside. Even though I brought 2 positive things in, I have 1 less positive thing on the inside. Okay, so that's just called a membrane potential. All right, so that plays a role in far more complicated biology, but not for you guys. All right, here we are. I don't know what to say. Endo and exocytoses. Can you tell me what those things are? That's what you got to do. That's the entirety of the rest of your test at this point in time. Like, legit, this is so simple because now there's nothing else to even think about. Like, once you have this stuff, right, the endocytoses thing is all that's really left. Okay? Like, that's it. You have words like bulk, transport, etc., but there's no complication here. It's not difficult. All right? I'm going to do a little drawing here. So that we can get a concept. Okay? So let's just do some general thinking. Cell. Food. Cell is going to basically reach itself around like this, okay? My drawing's terrible. To connect before this opens, basically what will happen is it will bring this inside the cell this way, okay? So the pictures that are on our stuff is far better than my drawings, but let's just put this together. If that's food and it comes in, is it endocytoses? Yes, endo goes inside. Is it phagocytoses? Yes, because it's food. Is it penocytoses? No, because penocytosis is what? Water. Just water. Phagocytosis is an endocytosis. Penocytosis is an endocytosis. Okay? Exocytosis, we basically only had one that we talked about. The idea of just putting off stuff and getting rid of things outside the cell. We'll go over that in a second. I'll show you. But just put phagocytoses as an endo and put peno as an endo. But know that they're different. Phago takes care of what? Food, right? And peno takes care of what? Basically extracellular fluids. Doesn't always have to be water, but it's liquid. All right, so it's easier to think of it as water, but liquid is basically what it is. It could be all sorts of liquids. that it's trying to bring into the cell. Okay, all for digestion, whatever else it may be. Several different things that are there. I have no idea. I hope to goodness this is not somebody that's sick today, because I'm drinking your Powerade. It's just that simple. Okay, so let's look at what our notes say about all that. When we move big things, we call that bulk transport. That's all that means, okay? Large things in and out, it's called bulk transport. As they're brought in, look what we get. We get a vesicle. In this case, we call this a phagosome, but a vesicle is all this is, right? Which is a closed portion of our membrane, right? You can see it here as it closes around this liquid. Here as it closes basically around the same type things that aren't food solid particles, but something else that we're trying to bring in, like an ion. We're doing that in this case because of a receptor, right? You don't even have to know hardly anything about receptor-mediated endocytosis because it's not even in your notes. It's here on the picture, but it's barely there, okay? So vesicles, endo refers to the movement of molecules into a cell. Phagocytosis is what? The process of doing what? Bringing in food particles. You can see it right here, food particles. Once surrounded by the pseudopod, the particle is enclosed in a membrane pouch called a vesicle. Even though this is a phagosome, it's still a vesicle, okay? Not hard. What do we call this? The eating or the drinking process of a cell. If it brought in food, it's what? The eating. Look, it's written right here. It's not complicated. Don't make this harder than it has to be. What are we going to do with this? Well, look right here. This is going to be on your test. What breaks down the stuff that's in here? So, remember, we talked about cell parts. Okay? We did. Cell parts. And as we talked about cell parts, we basically talked about a lysosome. And a lysosome does what? Breaks down proteins. Food inside of a cell. Technically inside of a vesicle. Like this, right? We've already brought it in. Phagocytosis has already occurred. A lysosome is here, and it carries enzymes. It will move over here and basically join like this. The membranes will dissolve in between. Whatever was inside the lysosome will then pour out the enzymes to go break down the food so that we can do what? That's right, so that we can basically take and do hydrolysis, the breakdown of things, so that we can get energy or whatever else that we need to get out of those things. Okay? A lysosome is what does that. That's what you saw on this previous slide, so make sure you know it because it's going to show back up on your test. Okay? I don't want us to be lost there, right? Lysosomes. Okay? Phagocytosis is the feeding process of a cell. Okay? That's all you got to know. Pinocytosis. It's a endocytosis in which we bring in what? Fluid droplets. You can see it right here. It's the drinking process of a cell. All right? Exocytosis is the movement of things out. Typically, it's going to come from their Golgi apparatus, right? That's our shipper. Remember our FedEx and our UPS truck? So it's nothing more than a vesicle that is then being sent out to the actual membrane. The membrane then connects it, right? Like this. No, I keep having to move y'all. Joys of technology. It's going to literally send a vesicle out to here. If it's connected to it, look, we still have a connected membrane, so our cell didn't bust open. Everything that was in it can then go outside. Exocytosis, the removal of things outside. What do we need to get rid of in a cell? All sorts of stuff. Things that this cell wants to send to another cell, sure. Things that this cell needs to send out to the extracellular matrices so that it can have signals that the cell is doing bad. Yep, absolutely, sounds great. Waste products, yep. Dead mitochondria that didn't survive and we tried to digest it and we couldn't get it all digested and we need to get rid of the waste. All's got to come out, right? All has to leave the cell. This cell's no different than us. We can't run around with waste in our bodies forever. We can't survive that way. Don't overthink that. It's just the removal of waste, right? Primarily. It's not always waste, but primarily. Okay. My hair is amazing right now. Oh, man. My face almost went away. Y'all wouldn't know what to do with yourselves if that happened, right? Okay. Here we are, transport vesicles. Now, let me ask this question again. What if I were to say exocytoses or endocytoses is responsible for the growth of a cell membrane? You should be able to tell me that it's what? Exo. We went and we put a vesicle against it, and then we opened it up, and that vesicle extended the distance. Whereas in an endocytoses, we grabbed around like this, and then we pulled it in until we found our own made our own vesicle. So we actually removed phospholipids off of that actual membrane. Okay, so if I were to ask you on the test which one of these two processes increases the size of a cell's membrane, it's exocytoses, and we do so because basically this portion of this membrane becomes now this new portion of this membrane, right? And guess what does that? The Golgi apparatus makes it available. It prepares this outside section to be able to go and to actually join here. Okay? That's all it does. And you're done. Now, before we run off, before you put your stuff up, don't move, because I'm going to put your test in my hand so that I know for a fact there is no discussion question that I just ignored on you. Okay? Because I want to make sure that you at least know those things. So, don't go anywhere. I'm going somewhere. You should still be able to hear me. Okay, so here we go. I told you about the 3 drawings. Done. Can you explain Turgor pressure to me? You should be able to, right? Occurs in what type of cells, what type of solution, and why would we want it? Those sounds like a very short answer for me. Can you tell me the difference between diffusion and osmosis? You should. Diffusion is the movement of what? Small things across a membrane. Osmosis is the movement of what? Be specific. Water across the membrane. Neither of them require energy. So I got to write down. That's it. That's not hard. Just write it simply. Let me know. Membrane potential. Can you explain the membrane potential? Again, remember, that is the difference in charges between what? The outside and inside, right? In active transport. You can see that on one of the previous slides. Okay? I already told you that I needed you to be able to tell me the difference between passive transport and bulk transport, or what we call active transport. Passive and active. One of them requires what? Energy. One of them does not. And lastly, why is facilitated diffusion considered to be passive transport? It doesn't require energy. You got it, guys. Yeah. I mean, I'm telling you, this test is very short and very straightforward. And it's because your notes are very short and very straightforward too. And I'd rather give you a short test and let you do well on it than put this test with another group of material, especially since the next thing that we're talking about is literally photosynthesis. So again, don't put this off until the night before. You should already be knowing this stuff and be prepared. If you've got any of those concepts, if you have any ideas about any of those things, you'll be fine. You'll be fine. Study it, do well. I pray that you do well. I miss you guys, even though I'm here right now and I'm going to see you tomorrow. I know that I'll miss seeing y'all. If I can be back early, I assure you I'll be back, because I would pretty much rather be here than be at home. That's simple. I'm going to enjoy my time with my father and hopefully be successful. But it's going to give me some time to kind of step away from the world and do some thinking, and not some thinking about what I'm going to do with my life. I pray that God leaves me here or in the role of being with y'all as much as I can, but I'm going to give me some time to kind of step back and to think about what God's done for me and how well he's taken care of me, and just consider myself to be blessed. So everybody do well tomorrow. Study hard. Please continue to remember to act right in front of everybody, but especially in front of my substitutes, and keep your head up. You'll be fine. Every single one of you will be fine. Don't panic. There's no need to lose your mind over it. You're going to be okay. All right? We're all good? Yes, no? You'll be fine. So I will see you guys. If you're watching this video, it's Tuesday. And that means I may not see you again until Friday. And I may not see you physically again until the following Monday. So we'll see how that goes. Pray for me that we're all safe and A-okay, and do well in your test tomorrow. I look forward to seeing some good grades when I get back. Okay? Peace out.